My name is Albert, and I'll be talking about sparse recovery for orthogonal polynomial transforms. This is joint work with collaborators from Stanford, Yale, and University at Buffalo, Anna Gilbert, Chris Ray, Atri Rudra, and Mary Wootters. In this talk, we'll first review the general sparse recovery problem, before introducing the specific class of transforms we consider in this work, and prior results for them. We'll then give intuition behind sparse recovery algorithms before introducing our formal results, and an overview of the main ideas behind them. In the sparse recovery problem, we're given an input vector x. We want to compute a given transform on this input, which is represented by matrix vector multiplication by a matrix F. We're interested in the case when the output y is sparse. These transforms, in the form of a matrix vector product, can often be viewed as the discretization of a corresponding infinite-dimensional functional transform. Let the dimensionality of this transform be n, and suppose that the output is k-Sparse. We are interested in sublinear algorithms. In particular, we are given query access to the input x, and we want to compute the non-zero y values. We want to do this in polynomial time in log n and the sparsity of the output. In the noisy version of this problem, the actual transform may not be exactly sparse. We call the largest values of the output y the heavy hitters. In the noisy setting, y is allowed to have some noise that is small compared to the k heavy hitters. In this case, we want to output a k-sparse vector z that approximates the transform y. In particular, we want the error between z and y, denoted by the blue shaded region here, to be small relative to the noise in y, shaded in green. This equation is the desired guarantee, which says that we want to find the k heavy hitters with error that's small relative to the inherent noise in the k-sparse output. Given query access to x, we again want to do this in polynomial k log n time. A rough intuition for how to break down the sparse recovery problem proceeds in stages by attempting to reduce it to the one sparse case. If this is solvable, we can hope to use a one sparse recovery algorithm as a black box to peel off a heavy hitter. This would leave a case minus one sparse vector on which we can recurse. However, existing sparse recovery algorithms do not explicitly make this reduction, even for simple cases such as the sparse Fourier transform. In this work, our first main contribution is to make this process a true black box reduction for a large class of transforms. Additionally, we will provide a one sparse recovery algorithm for a large class of transforms based on Jacobi polynomials. Combined with the black box reduction, this gives an end-to-end sparse recovery result for Jacobi polynomial transforms. Our black box reduction works on a very large class of orthogonal polynomial transforms. These transforms F are defined as a matrix of evaluations of certain polynomials at certain roots. We consider the case when the columns are indexed by a family of orthogonal polynomials, and the rows are indexed by specific evaluation points. Orthogonal polynomials more generally are families of polynomials satisfying a certain orthogonality property. Given a measure mu, which defines an inner product space on functions, orthogonal polynomials are an orthogonal basis for this function space. This inner product property can be discretized through their connection to Gaussian quadrature, which gives rise to the discrete transform here on the left. Their orthogonality makes them very useful as bases for function expansion, and gives them a number of useful properties and applications. For example, the orthogonal polynomial transforms defined here form a very broad class of useful transforms, just by specializing the orthogonal polynomial family. To give some examples, the classical discrete Fourier transform is a very special evaluation matrix, which are the monomials evaluated at the roots of unity, omega. Note that the discrete Fourier transform is over complex numbers, while we consider orthogonal polynomials over the reals in this work. However, many polynomial transforms are related in spirit to the discrete Fourier transform, so it is useful as a simple illustrative example. An example of a real-valued orthogonal polynomial transform, which can be seen as a real version of the DFT, is the discrete cosine transform. This is simply the orthogonal polynomial transform defined with respect to the Chebyshev polynomials. An important property that all orthogonal polynomials share is that they can be efficiently computed in a dense case. In other words, matrix vector multiplication takes nearly linear time instead of quadratic in the size of the transform. For example, the discrete Fourier transform and discrete cosine transforms just mentioned have fast algorithms, famously known as the fast Fourier and fast cosine transforms. This property holds more broadly for all orthogonal polynomial transforms. So the full result of a transform f times x can always be computed in time n times some log factors. We want to reduce the dependence from n to k in the case when the output is sparse. For sparse recovery of orthogonal polynomial transforms, the sample complexity has been largely pinned down. That is, sublinear queries to the input vector are enough to compute the k-Sparse output. However, these results generally don't give sublinear time algorithms for computing it. In other words, the time complexity is no better than computing the full transform, the O tilde n result for general orthogonal polynomial transforms. On the other hand, there are classes of algorithms based on Prony's method which work for general classes of orthogonal polynomial transforms in the case when the output is exactly k-sparse. However, these are not known to be robust to noise. In the setting that we are interested in, which is sublinear algorithms that are robust to noise, work has mainly focused on the sparse FFT. Only a few cases of real-valued orthogonal polynomial transforms have been analyzed, which generally reduce to the sparse FFT as a black box. To set up our more general results, we give a more detailed overview of the general idea behind sparse transform algorithms. Let's revisit an idealized algorithm, which roughly corresponds to the intuition behind some sparse FFT algorithms. It proceeds in the following steps. First, given the k-sparse output, we try to hit it with a filter, which can be seen as a diagonal matrix. This might reduce it to a one-sparse output y prime. Second, y prime is the transform of some other input vector x prime, and we'd like to use a one-sparse recovery algorithm to find y prime. In talks and papers, this step is often stated as a black box when given intuition on the algorithm. Finally, we can try to peel off this one-sparse vector, which leaves us with a k-1 sparse output to find. Now this can be found recursively. Although the flavor of this sort of reduction is implicit in some sparse recovery algorithms, they do not actually use a one-sparse algorithm as a black box. In particular, sparse FFT algorithms couple these steps using many properties specific to the Fourier transform, which makes it difficult to extend beyond the Fourier transform case. In order to make this reduction more explicit, we will need to be able to apply the one-sparse black box, which needs query access to the alternate input x prime. However, we only have query access to the original input x, so we will need to explicitly simulate query access to x prime using not too many queries to x. This is the main technical hurdle. Our results will make this black box explicit for a large class of transforms. The full sparse recovery result covers classes of orthogonal polynomial transforms defined by Jacobi polynomials. There is one caveat, which is that the k-sparse target needs to have spread out support. This is satisfied, for example, if the support is random. We'll elaborate more on this condition later. We note that this result includes a broad class of transforms, which includes essentially all the named families of interest and previously considered results. As mentioned, this result is factored into two parts. First, we show an explicit reduction for the sparse recovery problem using a one-sparse black box solver, assuming the heavy hitters are sufficiently spread out. This reduction works for essentially any orthogonal polynomial transform. There is also a technical condition on the roots of the orthogonal polynomials, but this is satisfied for all families of interest. Second, we provide an explicit one-sparse recovery algorithm for the Jacobi polynomials mentioned above. Combining this with the black box reduction gives the theorem. More formally, consider the one-sparse recovery problem, and suppose we have an algorithm for it, denoted A. Then, we produce an algorithm for the k-sparse recovery problem, using the one-sparse algorithm as a black box. This incurs an extra polynomial of k over epsilon factor in both the query and time complexity over the black box A. As mentioned, this reduction requires separation in the k-sparse output. Assume that all entries in the target output y are separated by at least a gamma fraction of the length of the vector. Then we incur a polynomial 1 over gamma factor in the cost. Note that a random k-sparse vector satisfies gamma equals 1 over k squared. Our second main result is a sparse recovery algorithm for Jacobi transforms. As mentioned, these transforms are a matrix of polynomial evaluations of Jacobi polynomials. For any fixed transform in this family, we produce a one-sparse algorithm with polylog n over epsilon query and time complexity. The assumption we required in our results is that in order to apply a filter for the reduction, the original output y must be spread out. This is true if the support was random, but to be fully general, we need a way to permute the support of these k-heavy hitters. By combining with the other techniques, one way to handle this issue essentially reduces to finding a class of permutations such that the permutation matrix times the transform equals the transform times the diagonal matrix. This is easy in the case of the Fourier transform, but we do not yet know how to do this for general orthogonal polynomials. Next, we'll cover some of the main ideas behind our results. First, let's look at the black box reduction. Recall that one of the main difficulties is simulating query access to the one sparse x prime, using not too many queries to x. Let's combine these equations to figure out what properties we need. First, invert the second equation to isolate x prime, and substitute the expression for y prime in. So with the substitution, we can relate x prime and x in terms of the diagonal filter. Now what we need is a handle on this product in the middle, so that a query to x prime can be simulated by a few queries to x. In particular, we need to find filters d, such that this product f inverse times d times f becomes row sparse. Then one query to x prime can be simulated by s queries to x. Overall, we'll need two properties for the filter, or this diagonal matrix. First, it needs to be able to isolate the heavy hitters, or elements in the support of y. In order to do this, it should look like a boxcar filter, which is roughly the indicator function of an interval. Second, we need the following product to be row sparse. Let's consider an element of this product more closely. Remembering the definition of the orthogonal polynomial transform, which is indexed by polynomials on the columns, this product has the form of the following summation. Crucially, if we choose the diagonal filter to also be evaluations of a polynomial, this summation can be written as an inner product in the original space defining this family of orthogonal polynomials. This fact essentially follows from properties of orthogonal polynomials and the relation to Gaussian quadrature. Finally, by the orthogonality properties, this will be 0 if the degree of the filter is small enough. This follows from expanding the smaller degree term in the orthogonal polynomial basis, which all cancel with the larger degree polynomial by orthogonality. This implies that the matrix is 0 for all entries far enough from the diagonal, which leads to the sparsity pattern shown in green. So, in order to satisfy these two properties, we just need a low-degree polynomial that looks like a boxcar. We can get a handle on defining these polynomials by leveraging results from approximation theory. In particular, given a desired approximation error epsilon, we have a desired smoothness of the filter. That is, we want our polynomial to be close to this boxcar filter in red. The desired smoothness controls the minimum possible degree of the boxcar polynomial by Jackson's theorem. And this translates to the row sparsity of the product that we need. So, equipped with these boxcar polynomial filters, we will be able to perform the stated black box reduction to one sparse recovery. To summarize, the problem is recovering the k-sparse transform y of an input x. We'd like to filter it so that the output is one sparse. This filtering step is where the separation property is necessary, so that the filter isolates a single heavy hitter, which raises the open question about permuting general orthogonal polynomials. We can write this in the form of a one-sparse recovery problem. Then in order to reduce it to a one-sparse black box algorithm, we need a handle on this product. By choosing the diagonal filters appropriately using properties of orthogonal polynomials, we can choose boxcar polynomials that have the desired filtering property, and such that we can simulate a query to this product with S queries to the original input. Finally, we'll briefly talk about the one-sparse solver for Jacobi polynomial transforms. Here's our one-sparse problem. Recall that the transform is a matrix of evaluations of Jacobi polynomials at certain evaluation points. We can invert the one-sparse equation, in other words, multiply by the transpose since it is orthogonal, to write the input x in terms of the one-sparse output. This means that x is just a column of f transpose, or a row of f. So x can be written as a vector of evaluations of the Jacobi polynomials at some unknown root, r sub I. Recovering the unknown index I of the non-zero element of y is the same as figuring out which evaluation point Ri this is. In order to solve this, we use the following steps. First, we have a rough handle on where the roots of the Jacobi polynomials are asymptotically. So searching for the unknown evaluation point r sub I is the same as searching for some unknown angle theta. By using asymptotic results for the evaluations of Jacobi polynomials, we can get a handle on these evaluations, which are entries of the input x. Now, by querying the input and combining sums and products of these queries, we get easier to handle estimates of the unknown angle. Specifically, we can get noisy versions of cosine evaluations at integer multiples of the unknown angle theta. Next, we use these cosine evaluations to narrow down the region of theta. Suppose that we looked at the first entry of the input x, which tells us a noisy version of cosine theta. Suppose that we know that cosine theta lies in this green interval. Then we know that the angle theta is somewhere in this region. Then we know that 2 theta is in this arc. But by querying the input again, we have a noisy estimate of cosine 2 theta. Say it's in this purple interval. Combining these two estimates tells us that 2 theta is actually in this region, which narrows down where we know theta can be. This process can be repeated to get our estimate of theta down to a desired accuracy. Backing this up, theta tells us the evaluation point Ri, which tells us which row of the transform matrix the original input x is, and this tells us the index of the non-zero in the one-sparse output y. In spirit, this process is similar to ideas used for the one-sparse FFT, but there are several additional challenges for the Jacobi case. For example, we have to sharpen existing asymptotics to handle the flatness of f. There are a lot of edge cases. In particular, the asymptotic evaluation formulas fail near the endpoints. Additionally, we can't actually obtain the cosine of every integer multiple of theta, and need to handle those cases specially. There is also a sign ambiguity in the inverse cosine function, which doesn't appear for the exponential function. However, these challenges can be overcome, resulting in a one-sparse Jacobi solver with query and time complexity of O tilde log n over epsilon. In conclusion, in this work we show a black box reduction for the sparse recovery problem to the one-sparse case, which works for general classes of orthogonal polynomial transforms operating on sparse vectors with separated support. We additionally show a one-sparse recovery algorithm for a large class of Jacobi transforms, leading to a full sparse recovery result for Jacobi transforms. Some open questions include, primarily in the filtering step, resolving the dependence on separation by finding a method to permute the indices for general orthogonal polynomial transforms. Additionally, we did not carefully track the polynomial exponent of these algorithms, which can be reduced. Thank you for listening.